and it's actually located in a very, very densely populated area. It's a city called Mannheim. Mannheim is the place where it is located. It's a very, very large city, and it's amazing. I mean, how they're able to maintain. It's more than 100 years old, and they have an interesting history that that's the only plant in the world there has not been a single explosion. That's amazing. I mean, they are able to. They have made sure that their processes are so very well understood, and their processes are so very well designed. Whatever transport processes you have been learning in this course, they have understood it so very well for their process, and they're able to control it so very well. That's quite amazing. I mean, it's very unusual to hear that there was not even a single small accident in the industry since its inception more than 100 years ago. It's a 15 square kilometer plant. So anyone who happens to be anywhere around that place, so apparently they have a tour for open for public one time in a week. I think Sundays. I think Sunday mornings they have an open tour for all the people from outside. So anyone who is actually going around that side, anywhere near Frankfurt, Stuttgart, any of these places, it's just a half an hour train ride. So you should go and visit this plant, and it's really a very pleasant experience. All right. Okay, so we've been discussing convection, and so let's a little bit of let's catch up a little bit, and then proceed further. So we stopped by observing some of these dimensionless quantities. Okay, we've been discussing the analogy between different transport processes. So we said that we define Nusselt number. Does anyone remember? Yeah? HL by K. What's that? Yeah? Minus? No, it's not. It's a positive quantity. What is it? It's the gradient at the boundary. I should rather say interface. It reflects the gradient at the interface. Okay, and similarly we could write, and that's the gradient, concentration gradient at the interface. What about CF? Yeah, tau by, so it's tau by rho u square by 2, and that will be 2 by Reynolds number multiplied by velocity gradient. At the interface. Okay. But we also defined this is the ratio of Nusselt number is a ratio of, right. So it's the conduction resistance in fluid divided by resistance to convection at rather across the interface, because you are really looking at transport across the interface. And similarly, one could have a definition for Sherwood number. We will not get into that, it is anyway similar. Now, we also said that what is the functional form of Nusselt number? So, remember we said that the temperature T star, the dimensionless temperature, is a function of x star, which is the position inside the boundary layer, right. So, this is Reynolds number, Prandtl number, and if you know the pressure gradient, it is typically a constant. So, Nusselt number will be a function of x star, Reynolds number, Prandtl number, and dP star by dx star. Because it is evaluated at the boundary, you take the first derivative. So, this is nothing but dt star by dy star, at y star equal to 0. So, the Nusselt number is not a function of y position anymore, it is only a function of x position, because you are interested in the gradient at the interface, which is y star equal to 0. Okay, so what we are going to see today is, so far we have not solved any equations. The question is, can we get any further insights without solving the equations? We have to solve them eventually, but we are going to first let us try to extract as much information as possible before solving the governing equations. Okay. So, the first observation is that the Prandtl number, okay, Prandtl number is a ratio of mu over alpha, which is the momentum diffusivity divided by thermal diffusivity. Okay. Now, note that all of these are happening in the boundary layer, right. So, you are looking at characterizing the process in the boundary layer. So, the momentum diffusion and the thermal diffusion, they have to somehow be related to the delta temperature. What is delta? Delta is the boundary layer thickness. So, all the processes, the momentum diffusion is occurring in the boundary layer, and it has to be a function of the boundary layer thickness, and the thermal diffusivity has to be a function of the thermal boundary layer thickness, because that is the domain in which these two processes are occurring. So, therefore, this is the general functional form. Okay. We do not know what that n is till now, we are going to figure that out while we discuss different aspects of convection. So, it is safe to assume that the ratio of the momentum boundary layer to the thermal boundary layer thickness scales as Prandtl number to the power of n. Okay, we still do not know what that n is. In fact, some of you who have already done this laminar and turbulent flow experiment in the lab, you must have seen some exponent like this, and so we are going to see what that exponent is. Similarly, one could express delta C as Schmidt number to the power of n. Okay. So, this also provides a mechanism to compare the boundary layer thickness, provides a mechanism or provides a method to compare the boundary layer thicknesses, and same here, right. So, immediately we could define, I could take a ratio of these two. Okay, I can say Prandtl number to the power of n, Schmidt number to the power of n. So, that goes as delta C by delta T. Okay. Let me make sure I think you get the numbers right. That is called Lewis number. Okay. So, this is basically 1 by So, defined as Lewis number is defined as Schmidt divided by Prandtl number. So, if we define a new number called Lewis number, what would be the definition for Lewis number? So, remember Prandtl is momentum by thermal diffusivity, Schmidt number is momentum by mass diffusivity. So, Lewis number will be thermal by mass diffusivity, okay. So, that is easy to see that. So, Lewis number is given by, that is momentum diffusivity divided by mass diffusivity multiplied by thermal diffusivity divided by mass diffusivity, and so that will be alpha by DAB, where alpha is the thermal diffusivity of the fluid that you are considering, and DAB is the equimolar mass diffusivity of the species that is diffusing in that particular stream. So, really what we have found is that Lewis number, Prandtl number, Schmidt number and Reynolds number, okay. That is based on the length of the plate, because we have looked at flat plate, you could always consider other geometries. So, these 4 numbers essentially characterize the diffusive properties of all 3 different transport mechanisms. So, you get a way by which you can compare all of these, which means that if you know one of them, if you know Reynolds number, there has to be some relationship between the heat transport and the mass transport processes. Each of these numbers, Prandtl, Schmidt and Reynolds number, they independently characterize each of the transport processes. So, this characterizes the thermal transport or the heat transport processes. This characterizes the mass transport process, and this characterizes the momentum transport process. Now, you may also recall that the governing equations that we wrote for these 3 transport processes, if we introduce the boundary layer approximation, they all look similar, right. They all have same terms, they have a convection term, they have a diffusion term, plus the momentum boundary layer equation has a constant which is the pressure gradient. Okay. So, the functional form of the solution for must be similar. Okay. So, it is very important to understand this, it is not same, it is similar, okay, because the momentum boundary layer equation does not depend upon the concentration and temperature, while the concentration and thermal boundary layer equations, they depend upon the velocity, although their functional form is same. So, therefore, the solution that you get, the functional form of the solution that you get, they have to be similar to each other, which also means that this also implies that if one of the processes is characterized, then other 2 must be similar, okay. So, that also means that because the functional form is same, So, if one of the transport processes is characterized, if I know how to solve one of them and I found the functional form and I found these dimensionless numbers, then I am done. I should be able to find the solutions for the other two. Okay. So, it is this property which leads to the concept of the boundary layer analogy. So, we are going to capitalize on this observation that the functional form is similar, and we are going to identify how to relate these three transport processes, and therefore, by characterizing one of them, we should be able to characterize the remaining. Okay, so because we said that the delta by delta t, which is the ratio of the boundary layer thickness, that scales as Prandtl number to the power of n. Okay. So, there have been lots of experiments, particularly primarily due to work done by Reynolds, where he has shown that the functional form dx star, okay, somehow it is found to be, in fact we will see in the future lectures when we take specific cases, we will see the kind of scaling that you will get. Prandtl number to the power of n. Okay. So, it scales as some function multiplied by Prandtl number to the power of n, and in fact that observation is because of the positing that the ratio of boundary layer thickness is scales as the Prandtl number to the power of n. Okay. And in, this may appear very heuristic right now, but you will see that in the subsequent lectures that almost all the geometries and all the problems you consider, this is the kind of scaling that you would usually get. Okay. So, for now we will assume that this is the scaling that you will get. Assume this scaling, in fact for different cases later. By the way, this has been experimentally shown very well. So, there are some nice cute experiments that has been performed, where you can see this kind of scaling has been observed experimentally for different kinds of problems. So, similarly you could assume, so therefore we said that the Nusselt number, okay, which is h into L by kf, so that is given by some functional form, okay. If I call this as, maybe I should use a different nomenclature, I call it G1, okay. So, x star REL and Prandtl number okay. So, that turns out that it scales as dp star by dx star into Prandtl number to the power of n. Okay. So, that is a, because of the observation that the functional form, the Prandtl number to the power of n scales out as a separate entity in the functional form, we should be able to write Nusselt number in simply as some function g1, which is going to be function of x star, which is the x position, and the Reynolds number and some pressure gradient multiplied by Prandtl number to the power of n. So, supposing if I assume that dp star by dx star is constant, which is a fair thing to say. So, Nusselt number can simply be written as x star REL into Prandtl to the power of n. Similarly, we could say that Sherwood number will be same functional form x star multiplied by Schmidt number to the power of n. Okay, any questions? Because the heat transport and mass transport in the boundary layer are related to each other. Okay. For the momentum boundary layer, we said that the friction coefficient, okay, so that's given by 2 by Reynolds number into the same functional form into G1 into X star REL. Okay. Now, if I am going to relate these three, how do I know what? This functional form would be just G1. Okay. Now, the reason is that if you remember the model equations, you will see that the scaling that you get in front of the diffusion term in momentum equation is 1 by REL, in heat transport equation is 1 by REL into 1 by Prandtl number, that is why. And in mass transport equation is 1 by REL into 1 by Schmidt number. That is why the functional form will be same. Okay. So, now we can relate these functional forms. So, we said G1 X star REL, okay. So, that should be equal to, okay, that will be CF REL by 2, okay. And suppose the Prandtl number and Schmidt number are 1. When can Prandtl number and Schmidt number be 1? When can that be? When can you have delta T and delta same? So, when Prandtl number is equal to 1, so remember that it is nu by alpha, right? Momentum diffusivity by thermal diffusivity. So, this is 1, which means that the momentum diffusivity is almost equal to thermal diffusivity. When is that the case? What kind of systems will have momentum diffusivity and thermal diffusivity equal? Or let us say momentum diffusivity, thermal diffusivity and mass diffusivity. I said Schmidt number also is equal to 1. What kind of systems will have I am saying that Schmidt number equal to 1, which is nu by D. Does anyone know? Any example of when can it be the case that the thermal diffusivity and mass diffusivity are almost equal? It is dilute gases. When you have very thin gas stream, so if you measure the properties of this thin gas stream, it turns out that these three momentum diffusivities are almost equal. They are not exactly the same, but they are almost equal. So, in those cases, the Schmidt number and Prandtl number are almost equal to 1. Okay.